Okay, so hello everyone. Today we are very happy to have Professor Brian Plancher to give us the autonomy talk. And Professor Plancher is an incoming assistant professor at the computer science department at Dartmouth College. And he's also, and there he will lead the accessible and accelerated robotics lab. And currently, Professor Plancher is an assistant professor at computer science and at Barnard College and also in the Department of CSEE at Columbia University. And Professor Plancher's research is focused on optimizing robotic system at all scales by, using algorithm, hardware, and software co-design. And Professor Plancher has broad interest in intersection of robotics and computer architecture, embedded system, numerical optimization, and machine learning. And today, Professor Plancher is going to give us a talk about the recent work about optimizing robotic system at all scales, and it will be very interesting and insightful. So, without further introduction, Brian, the stage is yours.
Thank you so much. That was very kind of you. Yeah, and I'll switch to slide two because you sort of told the story there, right? So I'll be moving to Dartmouth starting in the fall, but and I'll take the time just like I think who was it? It was a couple weeks ago. Somebody was like, "Oh, and hey, we're hiring PhD students at UBC." I think it was Alberto. We will hopefully be taking on PhD students up at Dartmouth. I'll leave that for the last slide. For now, let's talk about the actual talk. So let's talk about optimizing robotic systems at all scales. And so I'll do a little bit of an intro, we'll do a little background, and then we'll dive into sort of our case studies for today. Like probably many of you on this call, I'm pretty bullish about robots. I think they offer a lot of opportunity to do some really amazing things. We're seeing some really dynamic behaviors coming out of robots these days, and I think there's a lot of promise to hit those long-term goals of, say, home health aides or disaster response. Like we're getting closer and closer, it seems like every day, to making some of these amazing positive impacts a reality. And I just want to be clear that, like, while I'll talk about sort of capital R robots today, all the methods and approaches that we're talking about could be applied to autonomous systems sort of more generally. And what I mean is sort of any sort of system, any sort of cyber physical system where you have like interaction with the real world with some compute sitting in the middle where we're sensing things and we're trying to send commands to actuators. And so that could be something like, I don't know, a power grid or a chemical plant or any other sort of cyber physical system can be sort of controlled in these similar ways. And so if your interests are slightly more broad than sort of like capital R robots, hopefully this talk is still actually useful and interesting, to you. So robots are really cool. I hope you agree with me. They can do good things, but we still have a long way to go, right? We still have robots sort of falling on their head all the time. And to me, one of the major challenges here is just raw computational performance. And so sort of a motivating challenge for most of my research and my lab's work, which I'll talk about today, is sort of how can we enable the real-time edge deployment of computationally bounded robotics algorithms? And sort of as we were kind of mentioning in the intro, the way I go about trying to overcome these computational challenges is through algorithm, hardware, software co-design. And so probably maybe a new phrase for many of you. So what do I really mean by this? This is sort of coming out of a little bit of like computer architecture systems world where I spent about, sort of half of my PhD. And the idea here is, we have algorithms and they could be optimization-based algorithms, they could be machine learning-based algorithms, they could be some other sort of algorithm. And sort of the idea here is I want to think carefully about the algorithm, but I also want to think carefully about the software systems and computer hardware upon which these algorithms are going to be run. And I want to think about how these algorithms are going to run on this sort of hardware in the context of the applications that we're working on, which could be a whole host of different sorts of robotics applications, which come with their own constraints and their own strengths and sort of weaknesses. And I actually still need to layer one more thing on this, which is that I need to compute this in real time in order to make this work in this sort of cyber physical systems domain, right? And so when you do this sort of holistic co-design, you can come up with really interesting algorithm, robot, computer hardware pairings and redesign your algorithms to make sure that we can hit the metrics we need to get these robots out in the real world robustly and reliably. And so that's sort of the idea here. And so let me dive a little bit more into this compute box, because if we're going to talk about sort of designing our compute stack, we need to kind of understand what's exactly in here, right? And To me, I think about the compute inside of autonomous systems as sort of having a couple of different layers, right? There's some sort of middleware OS type thing that's doing a bunch of message passing to get in all the sensor signals and send it between all the different algorithms. Those algorithms could be sort of your more traditional perception, mapping and localization, planning and control, or it could have some amount of learning. It could be full end-to-end learning. It could be learning across a couple of those stages. All of that is sitting on top of some core computational kernels, which might be, say, physics, linear algebra, things like that. And those kernels are running on some computer hardware. And so this co-design idea is to try to break across that stack and think about how do we design like cross-layer things. Because many times folks are focused on an algorithm or they're focused on a kernel or they're focused on a hardware, right? And this co-design idea is how do we go across this? And so I want to provide you with a case study today of why I think co-design is exciting and why I think it can have impacts. And the case study we're going to do is sort of nonlinear in parentheses, model predictive control. And we're going to do two things with this. We're going to scale out on the GPU and go for large scale problems quite fast. And we're going to scale down and compress it onto a microcontroller and talk about how we can get this to run on a tiny robot, sort of at the extreme edge. And so that's like the high level plan and the high level motivation. But I do know also that this audience has a lot of different kinds of backgrounds and all sorts of things related to autonomy. So before I really dive into those case studies, I wanted to provide a little bit more background into this nonlinear parentheses model predictive control sort of paradigm. But want to pause quickly and make sure that there's no questions right now before I do any more background. And seeing none, please just jump in if you have any. I'll keep going. So model predictive control is a online control scheme that's used in many robots today, in state-of-the-art robots, right? And so this is, I guess at this point it's old version Atlas. We've now got a bunch of new version electric Atlas, but Atlas uses MPC to control its motion. And the way that they do that is you can compute a trajectory from a start state to a goal state. So here's sort of like a 2D cartoon, shall we say. And when we operate in the real world, maybe we have this plan and we're going to execute the first step of the plan. And no matter how good your plan is, no matter how good your simulator is, I promise you, you will not exactly hit the next step in your plan. There could be a little dirt in a motor, you might have a loose wire, the ground might not be as flat as you thought. If you're flying a quadrotor, there could be some wind, right? And no matter what you do, you're going to be a little bit off. And there's a lot of different ways you can try to fix that. And the MPC approach is just to say, I'm just going to replan. I'm just going to re-optimize my whole trajectory the rest of the way to my goal. And then I'll take another step and I'll replan again, and I'll take another step and I'll replan again. And this sort of online replanning process or online re-optimizing process is really the hallmark of MPC. And it's what makes it really effective, but it's also what makes it really computationally expensive. And that we need to resolve this full planning and control process online at every sort of control step. Now, what is this thing that we're solving? Okay, so the trajectory optimization problem that we're sort of optimizing at each of these steps is this big nonlinear, non-convex optimization problem. And what we're trying to do is we're trying to minimize some cost function across all of these states and controls. So you can think of each of these like little dots on the picture as a state control pair. So like in that state, we'll apply some control. We want to minimize some cost. And that cost could be something as simple as like distance to the goal. It could be like total torque if you're trying to minimize effort or something like that. And that's usually, user defined. That's going to be different for every sort of robot, but it's usually some sort of relatively simple metric. If you come from machine learning land, it's your negative reward. So we're going to minimize the cost. You usually maximize the reward in RL. It's basically just the inverse of that. Now, we have to minimize this subject to physics. If we don't obey physics, we're going to get garbage. In fact, the really kind of funny thing that happens here is if you sort of forget to include your physics constraint, the optimizer will usually return, great, I will have you teleport straight to the goal, which would be nice, but we can't do that in the real world, And you might have a more constraints. You could have torque limits, position limits, obstacle avoidance, all sorts of things. This is this giant math problem that we sort of write down and we're trying to solve online really, really fast. And so your next question is probably like, how do we solve this problem, right? Now, there's a lot of ways we could go about doing it. It turns out that most of the time when you're solving this trajectory optimization problem, it sort of breaks down into a three-step process, which I'll sort of call successive convex optimization. The idea here being it's very, very hard to solve. In fact, it's like NP complete to solve this full nonlinear problem in the general case with all of the nonlinear non-convexities that are in it. And so what we'll do is we'll iteratively try to like form a solvable problem. So we'll take maybe a quadratic cost and linear constraints. That forms a QP. So we'll compute this approximation step one. If we do that, we get this nice little bowl. So you can think of the solid line here as your sort of nonlinear function, and the little dashed bowl is our quadratic approximation. And so we'll just take gradient steps. So we'll just sort of go downhill, project, go downhill, project, and keep going. Now, sometimes when you do this, you might find a lower cost on your approximation that actually results in a higher cost on your initial problem. And so when that happens, we have to do some sort of a line search type technique to sort of back off the update until we actually end up with a lower cost. So at a high level, that's all we're going to do. And it's quite fast and it's quite powerful, but sometimes it's too slow, right? So even with this sort of approximate approach, even with this iterative solver, even with all the results that you've seen on real robots, this often doesn't fully scale to the full whole body case, the full nonlinear case. It's just still very computationally expensive. And so what I want to do first is show you a little bit about how we're trying to get around that by scaling out onto GPUs. But again, before I dive in, let me pause because I know that was like a lot of background content really fast. So does anybody have any questions sort of right now?
Can I ask you a question, quick question?
Yeah, go for it.
So you focused a lot on scalability of this problem, but even convergence is a big issue here. So there is no guarantee that if you do, you get really to the optimal thing, or even close to optimal thing, or how close we are. And that's
I think that's a really great point. So, I think there's a number of parts of this problem that are important to solve. I'm not going to touch a ton on general guarantees on nonlinear convergence, but I will tell you that we're going to do a little bit of theoretical work on how to make at least a linear system solves convergent. But yeah, I was trying to focus first. A lot of this work that we've been doing over the past couple of years was sort of inspired by the fact that people were like, you can't do this because you'll never be able to compute it, even if you could make it convergent. And I wanted to say, no, like let me show you how you can actually, this can be fast enough. Like we can solve this, and then we can go on and do a little bit more work to try to think about the more general case. So yeah, I will focus more on the scalability point, but I will throw in some theory here, and you should keep pushing on that. And if you like provability, let's talk later, because I would love to also scale up the sort of global generalness of these kinds of approaches. They are locally optimal approaches at their core.
thanks.
Yep. Okay. And yeah, I'm at ICRA this week, so I'm already starting to lose my voice. But if you're here and you want to bug me more in person, feel free to come find me around the conference. But I apologize, I'll probably be drinking a bunch of that water. So seeing no more questions, let me dive into our GPU side of things. Okay, so this is actually a plot that I really wanted to share because when I first saw this plot, it kind of blew my mind, right? So like when I was a grad student, I was like, yeah, our algorithm was too slow. Great, we'll wait for like the next generation computer and it will just get faster. And I don't know if many of you know this. I didn't know this at the time, but basically since around 2005, computers have not gotten faster. We sort of have maxed out our clock speed due to like physics limits and not sort of melting your processor. Now, the computer architects are working very hard and they've actually made some progress, right? And so the computers are a little bit more performant, but the scalability of that performance, this is a log plot here, is dropping. And so we aren't getting sort of the generational increases in CPU performance that we used to have. And so the way, if you have an algorithm that is too slow, you can't just wait for computers to just make it much faster. We have to take a different approach. And that approach, at least that most of the field has been going, is sort of parallelism, right? So that's my pitch on why you might want to consider parallelism. Now, before I can talk about co-design for GPUs, I need to give you a little introduction to GPUs in like one sort of high-level cartoon so you understand sort of where and why we're coming from. So if you think of a CPU processor core as having sort of like some amount of math unit. So that's like the ALU. You can have like some amount of green here that's doing math. You have some amount of yellow here that's doing memory. And then you have some amount of blue here that's allowing you to do like sophisticated computations and be efficient through general purpose code. A multi-core CPU sort of has a nice balance of these things. So this would be like a quad-core CPU, which is probably what's sitting inside of your laptop. each of these cores can do some math. Maybe there's a little bit of SIMD in each of those cores. They have a decent amount of cache. You have pretty sizable caches on a CPU, and the control logic is good. Intel and AMD have spent a ton of time thinking about how to make their CPUs, super performant. Now, when you look to a GPU, you see a very different design. Right? So the GPU design, basically, the long story short, lots more math, lots less other things, right? So we have a lot of little green squares here, so you can do a lot of math naturally in parallel, but this is at the expense of a lot less yellow and a lot less blue. And so the long story short here is GPUs offer much more parallelism at the expense of a much more rigid computational model. Each of those sort of rows of green squares wants to compute the exact same sort of operation. So they all want to do a plus, they all want to do a times. And as long as they're sort of all doing the same thing, they'll be performant. But if you want all the little threads to do all little different sorts of things, that starts to slow down on the GPU. And so when you think about trying to parallelize an algorithm on the GPU, we need to, or in MPC in particular, we need to answer sort of a couple of core research questions, right? So we need to think about co-designing our solver to exploit, on the one hand, this large scale but specific kind of SIMD parallelism on the GPU. We need to also, though, simultaneously look at the mathematical structure of that optimal control problem. And by the way, like if you dive into this solvers for optimal control problems, there's a number of algorithmic approaches you can use to actually solve that numerical optimization problem under the hood. And so there's actually a pretty rich design space with very specific amounts of sort of sparsity and parallelism that are induced by these different sorts of problem structures and algorithms and a particular computational model on your GPU. And so really what we want to do is see, like, can we expose a problem that basically looks like matrix multiplication? Because it turns out the GPUs are really, really good at that, because that is a large scale operation that is highly naturally parallel, in that when you compute matrix multiplication, sort of every output cell is a dot product of a row and a column. And so since everybody's doing dot product, that actually works quite well in this GPU, where basically you tell each green square, you do a dot product, you do a dot product, you do a dot product, and you just give them a different pointer to some different data. So how can we sort of, with that mindset, think about algorithm design in this MPC space? So the first thing we sort of realized here is that, as I was saying previously, most sort of numerical optimization algorithms can basically be broken down into that three-step successive convex optimization process. And it turns out that if you start to benchmark this in a parallel computing context, there's really two bottleneck steps. In forming that approximation, it is the computation of physics gradients. And in that gradient step, it's the solving of a linear system. And basically everything else can be seen as minor in this parallel computing world. So really what our research question becomes, and what I want to talk about, is how do we accelerate those two steps, right? And we won't have time to talk about both of them in detail, so I will mention the first one in just one slide, basically saying that for the physics gradients stuff, and you can totally look up the papers and the work, and we keep working on this library, we developed a code-generating library that does a bunch of algorithmic refactoring inside of rigid body dynamics algorithms to generate optimized GPU rigid body dynamics kernels that we can compute in parallel to compute all that approximation. And it works quite well. Now, believe me or assume that I'm telling the truth there. Let's say we've done that and it's super fast. We still end up now with this like QP problem that reduces to essentially solving this KKT linear system. And so the question becomes, how do we solve this specific linear system quite fast? And that's what I want to spend, I don't know, probably the next 15 minutes talking about. So let's say we're going to solve this problem. It turns out that there's iterative methods like precondition, conjugate, gradient are known to be GPU parallel friendly. These are iterative methods for solving linear systems that basically reduce down to a bunch of matrix vector products. And I'll show you that algorithm in a little bit. But we have two challenges for using it in our context specifically. And those two challenges are that we need a symmetric positive semi-definite system and a good preconditioner. So let me talk about sort of both of those things. So the first one is sort of, we need a linear system. If we want to use CG in particular, that is SPD at least. And our system is indefinite because of that sort of 0 in the bottom right corner. We can regularize it. We can also form the Schur complement. This is a linear algebra trick where you, instead of solving this linear system in one go, you solve it in sort of 3 steps. In our case, this works quite well. because as our cost function, and G is our like cost Hessian, is separable across time, inverting that is quite easy. And so now we just have to solve this one block tridiagonal Schur complement system, this S lambda equals gamma system. This is actually kind of nice because we've induced a specific structure. It's block tridiagonal. And so we can implement a structure exploiting solver. So what do I mean by that? So this is CG, don't worry about the details. The important thing here is it's mostly matrix vector products and vector reductions, which are things that parallelize quite nicely on the GPU. And in our case, since we have this block tridiagonal system, all of these matrix vector products are mostly like block row independent, in that like we kind of just have to do the 3 there, and you bring the vector over, and you sort of only need to share information across maybe a neighbor. And so this ends up being like a low communication overhead, very parallel friendly operation. And we know exactly where the zeros are. So we can actually hard code that and hard code memory structures into our algorithmic implementation. And so we do a bunch of these kinds of tricks in our underlying implementation to make everything a lot faster and then distribute it appropriately across the GPU. So we'll sort of send each of the cores in the GPU one block row to sort of deal with. And that allows us to keep a lot of values in cache and things like that. Now, let's assume we've done that. Let's assume that's good. We still have this problem of needing to find a good parallel preconditioner. And so for those of you that haven't been exposed to this before, the idea here is if you're trying to solve a system, AX equals B, you can solve an equivalent system if you have some magical matrix phi that's like roughly A. You can solve phi inverse A equals phi inverse B. Phi inverse AX equals phi inverse B. And the idea here is sort of if phi is like roughly A, then like phi inverse A is roughly identity, and you're sort of done. And so if you can find a good preconditioner that's like easy to invert, you sort of jump halfway to the solution, and you sort of make your whole problem a lot easier to solve. And this is true both in terms of, in our iterative approach, the number of iterations we need to use, but also just numerical stability, right? You will generate a better eigenvalue distribution, and there's all these sorts of underlying things where this is just like straight up a good thing to do if you can make sure your system is not terribly conditioned. Now, we're in this parallel computing context, so we need to find a good parallel preconditioner. And so if you look in the literature, many people will just use basically a diagonal or block diagonal preconditioner. They'll sort of say, well, if I just pretend that my matrix is diagonal or block diagonal, I can just invert each of those individual elements in parallel. So that's a really good parallel thing. This works well, it's fast, but my matrix is definitely not diagonal or block diagonal. And so there's a lot of these off-diagonal elements that you'll lose, and so it doesn't do a great job conditioning the system. There's also a bunch of these like alternating overlapping block preconditioners that you might find that try to capture some of that off-diagonalness, but they have a lot of heuristics, and they, sometimes they work well and sometimes they don't. And so we sort of ask the question of, can we do better? And per the earlier comment, here comes some theory for you, on how to design a good preconditioner, and hopefully this makes you in particular happy. So we looked into the literature and we found these polynomial splitting preconditioners, which are kind of nice because we now have sort of a trade-off between accuracy and computational complexity and sparsity. That is, like, as we go farther out on this series, we will converge to the actual like inverse. And so if we go farther, we'll condition the system better, but we'll need to spend more time. And it turns out our matrix will sort of get denser over time. And so you have this nice little trade-off here that we can, again, try to do co-design with and try to fit how far we go with the kind of problem that we're trying to solve. Now, you can't just split it arbitrarily. There is a requirement on the spectral radius to make sure that this is sort of a valid splitting. So this will be a key requirement that we need to deal with. So you can't just split your matrix however you want, but you can split it many different ways. And we have this block tridiagonal system, and so I went looking for block tridiagonal splittings that might be particularly useful in this case. And so it turns out there's one that's pretty nice. It's called this stair splitting. And the idea here basically is that you subtract off a couple of the specific off-diagonal elements, and you get left with this sort of staircase shape. Now, what's nice about this staircase shape is that it has a sparse analytical inverse. That is, the inverse is actually just another staircase. And it turns out it's also super parallel friendly in that the diagonal is just the inverse of the diagonals, and the off diagonals only have that like share with like one row up and one row down kind of thing. And so it follows the same sort of computational patterns as our whole Schur complement computation and all the sorts of nice block tridiagonalness of everything that we're doing. And so I got pretty excited about this conceptually and thought, hey, can we use this exactly inside of our PCG, right? Can we just sort of like skip this whole polynomialness and just like take the 0th order estimate of this and like, let's see if we can use it, right? Is this good for our problem? And it's sparse, it's parallel friendly, it's a valid splitting. So that seems pretty nice. Unfortunately, it's not symmetric. And so it turns out the kinds of iterative solvers we were using require a symmetric preconditioner. So this won't work, which was pretty disappointing. So then we started to think a little bit more, can we make this, like, what can we do? Can we adapt this to make it symmetric? And the first silly idea you might have that turns out to actually work quite well is that, well, the left and the right stair are sort of the transpose of each other. So what if we just like add them together and divide by 2? Now, by definition, we are symmetric. Hey, okay. So can we use this? This is sparse, this is parallel friendly, this is SPD, this is a valid splitting. And can we use it? Yes, actually, like we can use it. It works quite well. We actually started to just like run ahead with our implementation and using this sort of in practice. There is one challenge here. The spectral radius of the final condition system is maxed at 9/8, which is pretty close to 1, but not 1. So this means that conjugate gradient is not guaranteed to converge. In practice, it usually works just fine, but we don't have that theoretical guarantee. And per that earlier comment, we would like more theoretical guarantees, like especially if I can't make a theoretical guarantee about global optimality of the whole problem, since I'm only doing local descent, I'd love to at least be able to guarantee that the local linear system solves like will converge, right? And so we started looking and doing a little bit more work to think about, is there another way to leverage this sort of splitting to get to something that would be provably convergent, right? And so here's another silly idea for you. What if we just force it to be symmetric? What if we just like copy things over the diagonal once we do it? It turns out that's equivalent to adding the left stair to the right stair and then subtracting off the diagonal. And it turns out, if you do a bunch of math, that is sparse, parallel friendly, SPD, a valid splitting, and it will cap our resulting spectral radius at 1. So this is like theoretically optimal, which is super awesome. So this is our symmetric stair preconditioner, and this is sort of what we decided to then, run with. It's block tridiagonal. It fits the exact same parallel structure. It works perfectly inside our sort of structure exploiting solver design. So that's what we did. We have our structure exploiting solver with our nice theoretical preconditioner, and we started testing it on some sort of robotics problem. So here's like a 5-point pick and place circuit. We're solving thousands of MPC problems, thousands of trajectory optimization problems as you run MPC for thousands of time steps as we sort of keep going around this sort of loop here. And so one question you might have is sort of how well did we perform, right? So here's QDLDL. So QDLDL is the linear system solver inside of OSQP. Which is a state-of-the-art QP solver. And this is sort of time as you scale the length of the trajectory that you're solving at each time step. This is your average solve time. On the CPU, QDLDL is solving a factorization-based approach. It's a serial algorithm. And so as you scale the problem size, you scale the time. When we do our iterative approach and we leverage parallelism, we actually don't scale that same way. So while we're sort of at parity for a short horizon trajectory, we can be 3 times faster, 3.5 times faster for a longer horizon trajectory. Now, this is nice. We get speed ups, great. I probably wouldn't be talking to you about this today if it wasn't faster, but the thing that I think is more interesting is actually the distribution of solve times. So this is a CDF plot. And so what you have along the x-axis is the linear system solve time. And you can see the CPU is basically deterministic. There's like a little bit of jitter at the top, right? Like looks like the last 5% of solves are maybe a little bit slower. But for the most part, it is consistent at this one exact time, which makes sense because it's a deterministic serial algorithm. PCG, on the other hand, our approach is both much faster and much slower. Now, this might be a little confusing, but essentially what's going on here is we're doing this iterative process, and we're doing it until we get to a solution. And it turns out if your problem is very warm started, it's quite fast. And if it's very cold started, it can be slower. And if you look at sort of the trajectory that we're testing things on, essentially when it's on those sort of arcs of continuous motion, we have a very warm started problem and we exit really, really fast. And every time we sort of stop and completely change direction, we have a very cold started problem, and it takes us more iterations to sort of solve. And that's sort of what generates this distribution. And we can actually go a step further now for more fun co-design. And we can say in this conjugate gradient world, and here's the preconditioned version, but basically it's the same as the original version, there's this sort of while loop exit condition. And so we can actually tune the exit tolerance of our linear system solve with the convergence of the overall algorithm in our use case. And so if we like change this epsilon value, let's say we say, actually, I can deal with a little bit of a cruder linear system solve or an even cruder linear system solve, right? I can actually shift the distribution mass of my linear system solve time to the left and make my average solve time much, much faster, which is kind of cool. And so like for this 1e negative 4 exit conditioning case, we end up with like 65% of our solves, being much faster, than the CPU, being more than 10 times faster. And our slowest solve is only 2.5 times slower. And so we can actually get like very, very good performance. And right now we're looking into other ways to sort of play around with this distribution and think about how can we cap the tail and make sure that we aren't slower. Do you want to switch between all this sort of stuff? And so I found this plot to be very interesting. And I suggest this to you to like check your distribution and not just your averages, because that may lead to a bunch of additional fun research for you. So we take our linear system solver, we put that sort of in the middle there. We add on all of our fast computation of the gradients that I didn't really have time to share from our grid library. And then for the rest of it, it's like a line search. And for our line search, we just run every iterate in parallel. So we just fully parallelize our line search. You put that all together, and that's actually our MPC GPU solver. This is what we actually run MPC with. And this is the one that you should really care about, right? How does this actually perform, right? Your linear system solver is 3 times faster, cool. Tell me what my end result is. So here's what your sort of end result on performance is. So across the top here, I'm scaling the trajectory length of the problem that I'm solving at each control step, again, from like 32 to 512 points. And then on the left here, what I'm doing is I'm saying you only have 1 millisecond, 2 milliseconds, 4 milliseconds to solve this problem. As soon as you do that, please send the result to the robot, right? That maintains a 250 hertz kilohertz control rate. And if I put a 1 sort of anywhere in this table, this would be a real-time iteration scheme. So if you've ever heard of real-time iteration, a bunch of people use this. And the idea here is that this successive convex optimization approach, you can often get away if you're warm started and just like running this very fast with just taking one pass through and then just immediately sending it to the robot. Because the world is often changing faster than you can optimize your gradient descent. So just like take one step, send it to the robot. So 1 would be a real-time iteration scheme, and people use this sort of all the time. And the question is, can we leverage this GPU parallel scaling and speedups to do better than a 1? And the answer is yes. If you have if you are okay with 250 hertz control, which by the way is pretty fast, we can get 520 iterations of these successive QP solves in one control step. And if you're okay with a short horizon trajectory like 32 knot points, we also can still do that. And more importantly, or at least for me, what I thought was very fun is we can really scale this. So we can still hit almost 2 loops for a 512 knot point trajectory at a kilohertz for full nonlinear optimal control on this manipulator problem, which is really fast, in my opinion. So I was pretty excited by this, and it really shows the power and the scalability of trying to do this GPU co-design. That's sort of our like headline result for the first phase of the work. Of course, a bunch of people then come and they're like, hey, I don't need a trajectory that long or that fast. Why should I care? And my argument to you actually, and this was sort of the original purpose of this whole thing, was if we can solve one solve really, really fast, that's really big, then we can leverage our scalability to solve batches of slightly shorter solves also in real time. And so one thing that we're working on right now is exactly this, and trying to think about, hey, can I solve like 64 32 knot point problems in parallel, right? Can I batch over it and like batch over integer modes? And now I can go from like QPs to like MIQPs. Can I, batch over hyperparameter settings so that I don't have to do offline search for those, and online I can adjust to the best hyperparameter? Can I batch over sort of unknown disturbances to my system that I can't model or understand? Can I batch to speed up learning? There's a lot of different ways where this sort of parallelism and batching might be useful. And I think the best example of this is all of the amazing work coming out of like MPPI style algorithms, which are sort of using, you know, like a rollout batch. And here we can actually do batches of full trajectory solves. Right? And I have like one preliminary result for you that I can share, which is kind of fun, of using this on the robot. So here, the robot doesn't know that there is a weight on it. And as it moves around, it has no idea that it's pulling forces on it. And so if we just do one solve, we can't really model this in any way. We can try to sort of figure out what's going on and, you know, figure out like, oh no, something is wrong, right? Like, let me keep running MPC to react to it. And we can sort of get to some of these goals, but we have a really hard time trying to figure out what's going on because it's sort of yanking us in all these different directions. If I use a larger batch size, I can start to actually like grid search around possible distributions and then take sort of the moving average of the most likely distribution across all of my 8 solves. And suddenly I can actually much more quickly adjust for that and hit my targets. You know, now I could also use the force torque sensors on the robot, which we're, you know, ignoring at the moment, but this was more of just showing that we actually can find uses for these sort of batch solves. And we're building off of a lot of this on this real-time sort of control setup. And, you know, working on more hardware demos right now, right? More compelling hardware demos. That's just our little like, you know, preliminary result. And also more importantly, we're working on, you know, general constraint support, Python wrappers, test docs and examples, right? Like we have now this proof of concept solver that I think is pretty good and pretty fast. And our hope is that we can actually make this useful for all of you. So if you find this stuff exciting, if you're interested in using these sorts of software solutions, like please reach out to us. We've got some support from NSF and TRI, and we're actually like explicitly trying to make this useful open source software. We're also, you know, we've got some, you know, preprint early work on even better preconditioning. There are more fun things you can do to make your linear systems even better. And we're working on some sort of like risk sensitivity and minimization stuff as well, to sort of extend our algorithmic approaches. And ultimately, you know, the two key things that I'm hoping that we can hit, I don't know, maybe this summer, probably, you know, give me another academic year as we scale up our lab, but I think we can batch here to do whole body contact implicit locomotion in real time. I think we can do it. We can batch over the integer modes, especially on a quadruped. There aren't that many modes. We can do that sort of branch and bound search, and we can use this scalability to like run, you know, contact implicit MPC in real time, I think. That's the hope. And then on the flip side, right, the integration with machine learning is the big elephant in the room for all of, you know, robotics right now. And I think we can actually accelerate for like online actor critic RL by using these sort of batch solves to very, very quickly generate high quality examples for our RL behavior cloning type solution. So that's sort of what we're going on there. And that's, you know, the kind of long story here short is, yeah, I got a little time, is that's how we're sort of co-designing our MPC solver to exploit both this hardware and this algorithmic structure, right? And so we took the algorithm, we targeted the key bottlenecks, and what did we do is we developed both things that are GPU parallel friendly and, you know, novel algorithmically to get there and to make this work both on the physics level and this like linear system solver preconditional level. That's how we scaled out, right? So I want to pause for a second and see if there's some questions on that before I do want to leave some time to move to the compressed little side, but let's pause on the GPU stuff for a second and see if there's any questions.
There's a question in the chat. Although the question could be left to the end, but since it's about this part, so I think we can ask the question for now. So how do you actually implement these co-design problems, and how do you optimize over these different MPC parameters, kernels, preconditioner, and etc.?
Yeah, and I see the other question here is about end effector position and orientation. So we are working on all the orientation stuff as well. I think we did we like fixed the, I believe we fixed the orientation on that exact example, but we are working through all of that. And I think this actually gets into how do we implement all of this. So historically, we've actually been writing low-level CUDA kernels by hand or developing code generation to do that. And so starting from the physics library, we have like a URDF parser that then will generate like pro robot optimized physics kernels. We've then written a bunch of our own kernels for linear algebra and different ways to batch and distribute all of this. This is incredibly time consuming, and I would love to find a faster way to use it. And there's a lot of new tools coming out that will make this potentially easier, but sometimes a lot of these tools that make it quite easy hide a bunch of things, and you can't get that super high performance. And so we're constantly looking and trying to think about what's the right balance of, implementation time and overall performance. And so you'll probably see us do some work in warp and JAX and some other things as we go forward to try to get proof of concept stuff out faster. But ultimately, it seems like low-level CUDA is the only way to get the ultimate performance. And so I think those lowest level kernels will probably implement there. And then we'll try to wrap them in some of the rest of this stuff to make it more generalizable. Like per the Python wrappers, like I was talking with some of the NVIDIA folks here at ICRA, about how can we get, on-demand kernel compilation so we can get this sort of like pip installable at some point. And it turns out there's ways to do this through like PyTorch wrappers and stuff. So we'll get that. We'll try to get that out. But in terms of the implementation, by hand, very painstakingly by hand so far. Yeah, I think that answers all the questions for right now, but we can get back to more at the end. I think we still got like 15 minutes. So let me quickly, and I intended for this to be a little bit quicker, talk a little bit about the tiny MPC work, and then I'll open it up for a bunch more questions. So the previous part, just to like remind us of context, was how do we scale out and speed up this algorithm? But there's a number of tiny robots where we could never do this, right? Like we can't put a GPU on a crazy fly. The thing can barely carry a microcontroller, right? It's this tiny little robot. And I will point out, by the way, this is collaborative work with Zach Manchester in the Robotic Exploration Lab at CMU. So what Zach and I set out to do was to think about, could we fit something on here? Like what could we do? Could we get MPC to run on one of these little tiny microcontrollers that runs at megahertz rates? We're an order of magnitude slower than a CPU. And by the way, we have like many orders of magnitude less memory, right? Like we have 1 megabyte of flash, right? Not like a, I don't know, terabyte hard drive, right? We have 200K of RAM, not like 16 gigabytes, So what can we do in this case? So we looked back again to this sort of concept of algorithm, hardware, software, co-design. And so we looked back at our algorithm and we noticed that in many cases, we could just take all of the other constraints and separate them away from the cost function dynamics problem. And so what we're going to use is we're going to use the alternating direction method of multipliers, or ADMM. And so if we use the ADMM to sort of use ADMM slacks for every other constraint besides the physics constraints and the cost function, we induce a problem that sort of looks something like this, where we have this like cubic update for our primal solve, which is our physics constrained cost function thing, which we can probably do traditionally through like something like discrete time LQR. And then we only have to have a quadratic projection based sort of update for all of these other constraints in many cases. And so really, once we do this, right, all we need to figure out is how do we compress this cubic step down, and then the rest of it is sort of quadratic in nature, and actually we might be able to run online. And so our high-level solution to this is to leverage a little bit of offline-online compute. And so what we did is we said, well, instead of explicitly solving that primal problem, offline, we can pre-compute the infinite horizon gain and a number of these terms here. And importantly, you'll notice this like C1 term has this inverse in it. That's the thing that's driving the cubic complexity. Normally LQR, you have to invert some matrices as you go back down, but if we pre-compute and we fix certain parameters, we can actually online only have matrix vector product multiplications in our LQR recursion. So we end up with this compressed LQR recursion after fixing some of this offline. This means that now we're only at quadratic complexity because matrix vector products are quadratic in complexity online. And so suddenly we now have low compute complexity. We actually have a really low memory footprint because we just saved like 1K, 1P, 1C1, 1C2. Like we don't have one per time step. So we have a lot more memory and we have no division online. And this is really important because many of these microcontrollers are quite bad at division. Now this isn't perfect. We have like chosen to fix certain things offline, but we still have actually a lot of flexibility online to deal with like changing world environment and changing sort of constraints, as long as we sort of do this one fix on this K infinity game, which lets us then actually deploy this onto a Crazy Fly and run it at 500 hertz on board the Crazy Fly, which is pretty cool. What can we do with this? We can actually even support conic constraints. So here we actually, the red is the trajectory that we told it to follow. And then we placed a cone constraint on its flight path, and then it flies the blue nice helical trajectory down. And I think in the demo that I think won us the best paper predict last year, we can also do online dynamic obstacle avoidance, because we can continuously update the right-hand side vector of these constraints. We can say like, there's a changing obstacle coming at you, but we sort of fix this linearization on the control parameterization, which lets us then run this quite quickly. And so that would be my like 20-second summary of how you can like scale down and compress. But but we've done a little bit of recent work. So let me tell you one sort of extension, right? Because in doing this, in taking this cubic nature and compressing it to quadratic, we actually fix a lot of things offline. Right? We have one linearization, and importantly, we fix a lot of key hyperparameters. So in the context of ADMM, there's this important hyperparameter row. Details not that important, but basically every solver that's good and uses ADMM like OSQP varies this a lot per iteration. And so recent work, what we've done, and this is sort of preprint, hopefully coming out soon, is that we found a way to, again, leverage this concept of, pre-computing some stuff and updating some stuff offline to generate essentially some adaptive cache terms that we can then use to sort of update the stuff that we pre-computed offline at, again, quadratic complexity. And what's kind of fun about this is this increases our robustness of our solver to disturbances. So normally, if we ran this fixed solver, we can generate a bunch of really good demos, but if you disturb it enough, it will break. And now we can actually take, just have a fan blowing some wind around our drone while we're trying to solve these figure eights, and we can actually successfully execute these trajectories. Yeah. So not a ton of detail here on this side, right? Because I know we're running out of time and I want to leave some room for questions. But my key point being sort of, when we're on the GPU side, we did a lot of work to like scale out and map it to the GPU. And then if we go to a different piece of hardware, like a microcontroller, we can think about then how do we handle the fact that we actually will never be able to compute all of that. What are the things we want to compress and learn? What are the things we want to run online? And then how can we generate a setup that enables us to sort of hit all those sort of criteria that we care about, right? And that to me is the crux of algorithm hardware software co-design, and how we can actually go ahead and get really good real world results of optimizing robotic systems sort of at all scales, right? So that would be my key pitch for all of you. Now, before I finish, I do have to thank a bajillion people. It's been really awesome being at Barnard and Columbia over the past couple of years. I've been working with most of this work. In fact, I think almost all of the work that I presented was first authored by undergrads or master's students. We have some amazing undergrads and master's students, a ton of names here. Also, collaborators at other institutions, advisors and whatnot, but there's been a huge team behind sort of all of these efforts, and they've done some really amazing work. You can check out on our website. We've got other works. We have more things sort of in this vein. And, I would be remiss not to then leave as my last slide, my little advertisement being, we're moving to Dartmouth. We'll be recruiting some PhD students, next cycle. If you think this kind of idea of algorithm hardware software co-design is interesting, please feel free to reach out. We will be continuing on this line of work and hoping to drive some really awesome robotics demos and impact in the future. So thank you.
Thank you, Brian. Thank you so much for the great talk. It's just so nice. It's very interesting and insightful, and it's very exciting to see like a tiny crazy fly now can like do so much thing. I mean, do so many things. So, are there any questions from the audience? You can post the questions in the chat or directly like ask the question. Well, let me be the icebreaker. I have maybe a little bit silly questions for here because I'm not expert in this field. So, I saw you spend a lot of time talking about how to like optimize the co-optimize GPU and the algorithm to make the things faster. So, can we also include like CPU in the cycle, because like many algorithms they are like do not use GPU and mostly runs on CPU. So can we also do similar things on CPU and algorithm?
Yeah, we totally can. It turns out that like a lot of that has already been done, to be honest, right? There's a number of really awesome, so like rigid body dynamics, like Pinocchio library, phenomenal, right? Very cache aware, does a bunch of work. And on the CPU, you can leverage a lot of existing software like Eigen for math that will do some smart things, and all these sort of number of packages. And so, yes, you can absolutely play this game. You can also do a hybrid game where you do some of it on the CPU, some of it on the GPU, other sorts of things like that. There, you'll have to be careful though, because it turns out the IO overhead of just like shipping data between the CPU and GPU can actually be
Mm.
quite expensive. So you need to think carefully about what is your sort of interface there. And yeah, you can do this on other hardware too. We can go FPGA. I didn't like show the slides, but like we have done some work accelerating rigid body dynamics on FPGA, and there's some people working on some MPC stuff there too. And again, like each of these different kinds of computational platforms comes with a number of different strengths and weaknesses. And so you really just have to think about what's the right balance of things in that approach.
Okay, thank you. And I saw there's a question in the chat about if you change the tool attached to the end effector, or if you deal with different payloads with varying mass, how much resources do you need spend for pre-computing models?
Yeah, so I think here it's if we're going to take that as like something that's definitely going to happen, then we're going to want to probably think about what are all the different approaches that we want to use to designing our system. So like I would probably then not hard code certain things in the algorithm, right? Maybe take a little bit of trade-off in terms of slowing down an individual solve to give us the flexibility to parameterize sort of what's going on in the end there, right? And so maybe we now need to add into our physics modeling that there is a changing weight or changing disturbance on the end. And then how do we do that? So ideally, we would not have to spend a bunch of time online pre-computing anything, but instead allow like offline, think about designing the software stack to take that as a parameter so that it is instantaneously included in a sense, right? Probably like it will slow us down a little bit anytime you add a new feature because you can't hard code and optimize as many things. But yes, we want to do that. I had somebody yesterday being like, your physics algorithm doesn't let me, you know, change inertia parameters online to do, you know, co-design search over the physical parameters of the robot. Could you do that? Yes. I just need to expose like a new API to, you know, let those memory locations be changed, right? Like we can map that down into hardware. We can come up with ways to do sort of that and then just generate flows where it's like, do you want that? Okay, we'll be like, you know, 2% slower and give you that ability. Do you not want that? Great. We'll stay at like 100% speed, you know, and hard code certain things. So I think there's a lot of rich options to implement all of these things. Please reach out if you want some of this stuff. We have a limited team and limited time, but if like 10 people say we want this, like we would love for our stuff to be useful. Like my whole point is I want to make software that will help all of you. I don't want you to have to necessarily do this and implement it yourself. So tell me what you want. We'll try to do it. And we're trying to scale up our team. So hopefully we'll have a bigger team and then we can get more done faster soon.
Nice, nice. Thank you for the great answer. Yeah, I really looking forward to the new results, and yeah, this is very super interesting. And all the audience can find your emails on your website, right? Oh, I saw there's another question
Yeah,
in the chat
yeah, I
about.
see that. Yeah, which
Okay.
GPU do? Yeah. So there was the timing results. I believe we were running that on a desktop that had like the 4090, like a nice big desktop GPU. But there's no reason you couldn't run this on like a Jetson as well. The main difference between the different GPU models, in our case, is actually not the memory. It's going to be the number of actual cores on the GPU. And the way we've sort of designed the software, like each GPU actually has a different amount of physical compute cores. And so the more of them we have, the longer horizon trajectory we can easily scale to because we can essentially just distribute like one knot point per core, or sometimes more than that. But like a simple way of thinking about it is like sort of one knot point per core. So as we scale down the GPU, we probably can't be as fast for super long horizon trajectories, but if you're comfortable with the shorter horizon trajectories, you can immediately take this and run it on a much less resourced GPU. Now, some of them also have slightly different clock speed, so it might be like a little bit slower, but like it should scale to the shorter horizons relatively performantly, even on something like a Jetson. And actually, to the question from earlier, the Jetson actually has a fused RAM that's shared between the CPU and GPU. So you don't have the penalty of I/O of shipping the data, you know, back and forth between the CPU and GPU. So in that case, not only can we a hybrid CPU GPU will just be much faster, right? So we lose a little bit of our scalability on the GPU having many more cores, but we don't have this high overhead, right? This is why this is a very rich design space, and I think we need to move towards tooling, you know, and like code generation and compilers and things to allow us to efficiently and effectively deploy across these heterogeneous hardware architectures. Can I guarantee constraint satisfaction in the future? And do you run into incompatibilities? Yeah. So if you as we are doing sort of, this linear quadratic approximation, you can always generate an infeasible problem in that the linearizations of your constraints could be conflicting. Now, depending on how we implement that constraint satisfaction, we can get around that by softening some of the constraints and allowing for slight constraint dissatisfaction to get the whole thing to solve. If you actually look into solver papers, right? If you look into like the depths of like SNOPT and IPOPT and whatever, they have like crazy sets of parameters and crazy amounts of detail because all of these commercial solvers do a ton of tricks to try to prevent exactly that from happening because they want to be general to any sort of use case. If you design your problem well, you won't run into many of these incompatibilities, but if you don't, we'll have to throw in a lot of tricks. Will our first generation open source software support every single trick? Absolutely not. I would love to, but there's no way that we'll have the time to do it. But I promise we'll do as many as we can, and we'll keep adding it sort of as we go. And these are good things to sort of think about as you generate these problems. And I think, again, this is where like this cogeneration software flow is really important because probably where we'll start is we'll be like, you can implement these kinds of constraints. And maybe what we'll try to do is some offline checks to like guess if generally you're going to run into issues or not and warn you, and then we can go from there and adding in more and more features and more features. It turns out if you add in like all of the features, unfortunately, then you slow things down too. So there's, again, going to be always this trade-off in terms of what are you deploying to, in that like, do we have extra time to do this, right? We can do a bunch of maybe parallel and feasibility checks on the GPU, but I kind of don't want to do any infeasibility checks on the microcontroller because I can barely get the darn thing to compute the problem to begin with. So again, sort of, trade-offs. How do I best get updates on my future work? Oh, check out our lab website. I will try to post there as much as I can, or just email me if you want to work on any of this stuff. Like we're always open to collaborators. We do a bunch of work with people at a bunch of different schools on different things because there's so many pieces to this, right? Like the preconditioner work, we're working with some folks at EPFL right now in Colin Jones's lab, trying to think about, the math and the control theory, right? Like I'm talking with James Anderson at Columbia on the small scale system side about integrating some learning stuff. Like we're working with some computer architects at BU and Sabrina Newman's lab and at Harvard and VJ's lab about, some of this FPGA and compiler stuff. So there's infinite work to collaborate. I keep working with Zach, tons of people. Like I love collaborating. And I think in this space that's so rich, we have to achieve a lot. And so, yeah, please do reach out, check out our website, like bug me. I'll try to get back to you as soon as I can. I'm at ICRA. If you're at ICRA, come talk to me. I'm here all week. We actually have a workshop on Friday on the intersection of robotics and computer architecture at ICRA. I'll be running that all day. So come to that. We generally run that also at Micro, which is a computer architecture conference. So there's lots of opportunities to join the community. We sort of have this little niche of co-design here that we're kind of trying to grow because I think it's going to be important to have high performance software systems if we want to hit the kind of performance we need for robotics at the edge.
Nice. Thank you for the very fruitful discussion. And any other questions? Well, we have already run out of time, so thank you so much for the great talk. It's super insightful, and we can see there are great potential in this field, and really looking forward to your future works. Yes, thank you again.
No problem. Have a wonderful day.
You too.